Welcome, everyone. Today, we are going to explore the journey of building robust and maintainable systems in Rust. As projects grow in complexity, developers often face the challenge of spaghetti code, where tight coupling makes the codebase difficult to test, modify, and scale. Our goal today is to move toward the gold standard of architecture, shown on the right side of the slide. We will focus on architecting scalable Rust backends by mastering two core concepts: the facade pattern and sophisticated dispatch strategies. By leveraging Rust's unique features, such as traits for abstraction, dependency injection for modularity, and async orchestration for performance, we can create a clean, structured interface that acts as a gateway to our logic. This transformation ensures that your backend remains flexible and resilient, providing a clear path from chaotic, intertwined dependencies to a highly scalable and professional architecture. Let's examine the God handler anti-pattern, a significant architectural pitfall where a single API route handler assumes far too much responsibility. As illustrated in the diagram, the handler is directly intertwined with the Postgres database pool, the Stripe payment client, and the shipping calculation logic. This degree of tight coupling creates three critical issues for long-term maintainability. First, it results in a testing nightmare. Because the business logic is not isolated from infrastructure like the database, it becomes nearly impossible to write clean unit tests. Second, we face substantial refactoring friction. If we need to change how we interact with a third-party service like Stripe, we are forced to rewrite parts of the HTTP layer itself. Finally, this pattern imposes a heavy cognitive load. The handler possesses too much knowledge about various infrastructure components, making the code significantly harder to understand, maintain, and evolve over time. To simplify our architecture, we implement the facade pattern. By definition, this is a structural design pattern that provides a unified interface to a complex set of internal modules. In this diagram, the client, or API handler, interacts solely with the facade, which functions as an orchestrator. This facade manages the intricate interactions between various subsystems, such as inventory, payment, and shipping. The primary benefit of this approach is that the handler only needs to call a high-level method, such as processor.placeOrder, allowing it to remain completely ignorant of the underlying plumbing and complexities within the subsystems. This basic blueprint illustrates a concrete facade pattern using an order processor facade struct. This struct aggregates several subsystems: an inventory system, a payment gateway, and a shipping service. The primary advantage of this implementation is seen in the place order method, which serves as the single entry point for client interactions. By encapsulating the orchestration logic, such as checking stock, processing payments, and arranging shipping, the facade abstracts away the underlying complexity, providing a much cleaner interface for the call site. However, as noted in the takeaway, this specific implementation introduces rigid coupling. Because the struct directly owns these concrete types, the components are tightly bound together, making it difficult to swap implementations or use mocks during testing. To integrate our facade into an Axum application, we begin with state injection. First, we wrap the order processor facade in an ARC, or atomic reference counter. This is essential because Axum requires application state to implement the clone trait. By using an ARC, we ensure thread safety and allow the facade to be shared across multiple request threads efficiently without performing expensive deep copies. Next, we inject this shared state into our router using the .withState method. This makes the facade available to any handlers defined on that route. This setup enables us to write what is known as a one-liner handler. By utilizing the state extractor in the handle order function signature, we can pull our facade directly into the handler. This transforms the handler into a thin pass-through layer that simply delegates incoming requests to the facade's place order method. This pattern effectively decouples our web-specific routing from the underlying business logic. Decoupling with traits allows us to move away from rigid, concrete structs and toward more flexible, behavior-driven design. On the left, the concrete struct is depicted as a solid, brittle block that is prone to cracking when changes are required. This represents a tightly coupled system where logic is hard-coded to specific data types, making the architecture difficult to scale or modify. By extracting these behaviors into traits, as shown in the central code snippet, we define clear contracts like inventory and payment. These traits specify what an object can do, such as checking stock or processing a payment, without dictating the underlying implementation details. On the right, we see the trait represented as a clean, structured blueprint. This abstraction provides a stable interface that any struct can implement. The primary architectural goal here is to ensure that a facade or high-level component only cares that a specific action occurs, such as a payment being processed, rather than how it happens. This allows us to switch between different providers, like Stripe or PayPal, without needing to rewrite our core application logic. Dependency injection allows us to decouple our business logic from its underlying implementations. By looking at the dynamic facade on the left, we see that the order processor facade uses dynamic dispatch via dynamic trait objects. This structure ensures that the inventory, payment, and shipping modules are not hard-coded, but are instead swappable dependencies. Moving to the right, we can see how this architecture empowers our unit testing strategy. In this specific test case, we are simulating a payment failure. Instead of relying on a real payment gateway, we inject a mock payment object configured with a failure flag. This approach allows us to verify that our system correctly handles errors without ever making an external network call. Ultimately, by utilizing mocks through dependency injection, we create a test environment that is both deterministic and highly efficient. In this slide, we examine the practical implications of asynchronous programming and parallel execution. When tasks are executed sequentially, the total duration is the cumulative sum of each individual task, in this case, checking stock followed by getting a quote. However, by leveraging parallel execution with Tokyo Join, we can run these independent I/O tasks simultaneously. As illustrated in the timeline comparison, this reduces the total execution time to the duration of the longest single task, rather than the sum of both. Looking at the implementation details, we define an asynchronous trait for our inventory using the async trait macro. Within the place order function, we utilize Tokyo Join to concurrently execute check stock and get quote. This pattern is highly efficient for I/O-bound operations, where the CPU would otherwise be idle while waiting for network responses. Finally, it is crucial to note that traits must implement send plus sync to safely move across threat boundaries, which is a standard requirement when working with multi-threaded runtimes in frameworks like Axum. Let's examine the trade-offs in the ongoing debate between static and dynamic dispatch. On one side, static dispatch through generics uses monomorphization. This provides high performance by allowing for inlining, but it results in larger binary sizes, a more rigid architecture, and what is often described as generic soup in the codebase. Conversely, dynamic dispatch using objects like box relies on vtable lookups. While this involves pointer chasing, it produces smaller binaries, offers high flexibility, and keeps type signatures clean. To provide a reality check on performance, we have to look at latency and context. A typical database call takes approximately 5 milliseconds. In contrast, the overhead for a vtable lookup is roughly 5 nanoseconds. This means the overhead is 1 million times smaller than a single I/O operation. For the vast majority of I/O-bound applications, this difference is entirely negligible. Our verdict is straightforward. Use dynamic dispatch for standard backend development to prioritize code cleanliness and flexibility. Reserve static generics for library development where every nanosecond of performance is critical. Static dispatch offers a zero-cost alternative to dynamic dispatch by shifting the computational overhead of polymorphism from runtime to compile time. As illustrated in the code snippet, we define a generic struct, order processor facade, which utilizes generic type parameters I, P, and S constrained by traits for inventory, payment, and shipping. Rather than relying on runtime lookups via trait objects, this approach uses a process called monomorphization. During compilation, the compiler examines every instance where this generic struct is used with concrete types. It then generates unique, specialized versions of the code for each specific type combination, shown here as different configurations like Facade config 1 and Facade config 2. Because the compiler knows the exact types involved at each call site, it can perform highly effective optimizations, such as function inlining. While this results in superior execution speed and predictable performance, it is important to manage the trade-off, as generating unique code for every combination can significantly increase the final binary size. The facade and factory patterns serve distinct roles within software architecture. The facade pattern is classified as structural and can be compared to a car's dashboard. Just as a dashboard hides the complexity of the engine, a facade orchestrates and wraps various subsystems to simplify how a client interacts with them. Conversely, the factory pattern is creational and operates like an assembly line. Its primary action is to instantiate and return objects, with the ultimate goal of hiding the complexities of object creation from the user. The architecture presented here represents a robust pattern for building modern, high-performance web services in Rust. The process begins with an incoming HTTP request being routed to an AXM handler. To maintain simplicity, the handler delegates its core responsibilities to an async order facade wrapped in an atomic reference counter. This facade acts as the orchestration layer, handling complex tasks like business error mapping and concurrent execution via Tokyo.join. By utilizing dynamic trait objects such as boxdyn inventory, boxdyn payment, and boxdyn shipping, we decouple our business logic from specific infrastructure like Postgres, the Stripe API, or Redis. This design philosophy yields several critical advantages. It keeps our handlers clean and focused, ensures the entire system is easily mock-testable, enables efficient parallel I/O operations, and provides a unified strategy for mapping low-level failures into actionable business-level errors.